Hi everyone and welcome back to PrepFusion. I'm Anish and today we will start with the lecture 60 of electrical machines subject. Today we will be discussing about parallel operation of alternators, also what is meant by Droop characteristics and a few synchronizing techniques. If I want to connect two alternators in parallel with each other, how can I synchronize them? So before starting, I will highly suggest everyone to revise the lecture parallel operation. I will like pause the video and please have a go and look at the notes of parallel operation of transformers. If you can watch the lecture, that also will be good. Okay, but at least have a notes ready. At least go and see the notes of parallel operation of transformers. Single phase transformer will suffice. Okay, so same thing whatever we have discussed in parallel operation of transformer, same thing will be applicable. So if I have a single generator here and let's say this generator can supply 100 kVA of apparent power, right? And my loads are connected here, let's say some 60 kVA and 80 kVA. So of course a single generator will not be enough. I need to add another additional generator so that this also can supply some amount of power, so that we are able to meet the load requirements. So that is one of the reason, right? That is one of the reason. What are the other reasons? What might be the other reasons to provide a generator in parallel? So other reason can be that maybe sometimes what used to happen in is when there is high loads, right? Then I can operate both the generators in parallel. When there is light load, right? If there is light load, let's say this is 100 kV, right? Now my system, let's say, is rated for 200 kV. My system, let's say, is rated for 200 kV, right? Because 100 kVA and another 100 kVA is 200 kVA, right? So for this system, what is light load? Light load would be 20% or 40%, right? 20% of this overall load, 20% will be 40 kVA. So let's assume that currently a 40 kVA load is connected. So actually what I will do, I will not operate both the generators. I will turn off one of the generators and I will turn on the other generator, right? Why? Because we know that our generators or any machine that we make operates the most efficient way when it is like 50%, 60%, working at around 70 to 80% of its rating, right? Rating voltage. So this is actually good. Here, what is overall rating? 100 kVA, and according to that, if it is lightly loaded, that means 20% it is loaded, that is 20 kVA, right? So if I turn this generator off, it is supplying 40 kVA, the efficiency will be much better than this configuration where 100 kVA, 20 kVA it is supplying, right? So that is bad actually. Efficiency is not good. Okay, so that is also another reason that we operate generators in parallel. So there are many reasons. Okay, there are many reasons to operate generator in parallel. These are the things. Okay, now if you remember in transformer, right, in transformer lecture we had derived the expression for ea, eb, all these things were there actually. I will not again solve it, all these have been solved in transformer. Okay, so this was the case when I had impedance. Okay, impedance was a combination of resistance and reactance. But in case of a synchronous generator, generally we neglect the armature resistance because the reactance is very large. So just give me 1 second. So this will be this will be what? This will be J XS A. Okay, and this will be EA. Another generator will be connected basically. this will be EB, and here the load is connected, that is VT, and this is grounded, let's say. Okay, and load, like load is connected. I don't care about the load, so some load will be connected here, right? ZL, I don't care about that. Okay, for now I'm discussing regarding the circulating current. I'm discussing regarding the circulating current. What will be the circulating current? Okay, how can I find out the circulating current? So let us first discuss, if it is at no load. If it is at no load, then can you tell me what will be the circulating current? Again, we want to reduce the circulating current, right? If there is circulating current, what will be the problem? There will be huge losses here, right? We don't want it. So remember, now phasors are involved. Okay, even if the magnitudes are same, phase must also be same, otherwise there will be problems. Okay, so let's assume that at no load, right, there is some circulating current IC that is flowing, and we don't want this because there will be like, we don't want this generator to supply to the other generator, we want it to supply to the load, right? So we don't want this circulating current to flow, but that will happen. So what will be the IC basically? So IC will be, let's assume that both are same synchronous reactance, so IC will be EA minus EB divided by EA minus EB divided by 2 XS. Okay, divided by J2 XS. Okay, so now what we can do is, this is my IC current. Now I want to uh, yeah, now I want to see like what is the power absorbed basically. How do I calculate the power absorbed? How can I calculate? So let's assume that there is phase difference, right? Let's assume that even though the magnitude of EB and EA are same, but there is phase difference. What do I mean by phase difference? Let's say that my EA is here and my EB is here, right? So there is a theta c difference between them. Okay, and my IC is, let's say, somewhere here. Okay, will it be, it should be lagging current, right? It cannot be leading current, it has to be lagging current. Yeah, IC will be somewhere here. Okay, so what will be the power? So this, right, this will be, let's say this is theta b. Okay, and this is theta a. So how much power will be delivered by EA? Because always remember, power flows from higher angle to lower angle. Power flows from higher angle to lower angle. So as I know, EA is more leading than EB, so power will flow from EA to EB. So power delivered, it is open ended, it is no load, so here current is 0. Okay, power delivered by EA, okay, is equals to EA IA IC cos of theta A. And power, like of course none of the power is flowing here, right? So power absorbed by EB will be EB IC into cos of theta B. One more thing is, we know if I have two potential, right, and there is a angle difference between them as theta C, I can write the power transfer between these two. What is the power transfer? If you remember, the power P was equals to EF Vt by XS sin delta, right? So if this was the configuration, this was E angle delta, and here I had some JXS, and here I had Vt angle 0. So for this particular scenario, the power was EF or E Vt by XS into sin delta. Okay, EF Vt by XS sin delta. Okay, now next what I can do is so what will be the power in this case? Here what is the phase difference? Theta C. What is the potential? EA EB, right? So it will be EA EB by what is the like synchronous impedance between them. So it is XASA plus XSB, right? Or 2x. Okay, so 2 into XS into sine of the angle between them, that is theta C. Or I can directly write it is theta A minus theta B. Okay, I can directly write theta C is equals to theta A minus theta B. Okay, so this also, like you can equate this, and from here you can absolutely find out the power delivered or power absorbed. Okay, so all this can be asked MCQ, as MCQ all this can be asked. Okay, so I hope it is clear now. How can we find out the power delivered circulating current due to the power transfer if it is no load? If it is connected to a load, then how will you calculate? So for like basically if I have load connected, then you have to simply apply KVL KCL, right? So if I have load connected here, you simply apply KVL KCL. If I have load connected, you apply KVL KCL to find out the values. Okay, formula, remembering the formula is very difficult. KVL KCL, something you will get in the question, you will get a hint. Okay, so these formulas, I hope you are clear. I hope you remember that how much power will each generator supply is inversely proportional to their impedance. Okay, own impedance, or here in this case it will be inversely proportional to the reactance. So how much apparent power each will send is inversely proportional to the reactance, in this case synchronous reactance. Okay, because mostly synchronous reactance is present, Ra is 0. Okay, that is the important part to understand over here. Okay, I hope you have understood this thing. So these are the advantages basically. I will not explain, already it is written and you know all these things already. We have discussed about this in transformers. I will quickly go through this. Okay, so now let's understand few things, the characteristics of parallel operation. The parallel operation, right, I can vary few things. So first thing is I can vary the torque input to the generator. If I vary the torque input to the generator, then what will happen to the parameters, right? That is what we want to understand. Also, if I vary the field excitation current, then what will happen to the parameters, that also we want to understand. Okay, so first of all we will examine the effect of changing mechanical torque. Okay, at no load, we will see at no load what is happening, the effect of changing mechanical torque if it is not connected to an infinite bus. Okay, so if it is isolated system, okay, at no load, isolated meaning that it is not connected to any infinite bus, simply two alternators are together connected. Then what will happen uh, if I'm changing the torque? Okay, so here EA is here, it is not connected to any load at no load. Here EB is here, this is JXS, this is JXS, this is VT. Okay, so what we have to do is we can, if I am changing the input, right, initially both alternators will be running at synchronous speed with their frequencies identical. There is no phase difference because there will be no power transfer between them because everything is matched, everything is synchronized. If the mechanical torque input of one of the alternator, let's say this alternator A, is increased, then what will happen? While the other input torque here remains same. If I am increasing the torque, that means what? What is torque? Torque is proportional to, if you remember, torque is proportional to PE minus PM, right? If I am increasing the torque, that means PE has to increase. And how PE will increase? PE is proportional to sine of delta. So sine delta has to increase. Everything else is constant, right? Excitation is constant. So delta will increase. Delta increase means this now will have higher delta angle. Delta A will be higher than EB. Previously delta A and delta B were same. That's why there was no power transfer, right? Delta B. So now delta A will be higher than delta B. Then what will happen? Simply this will transfer power from alternator A to alternator B. So a IC current, circulating current will flow. That's it. Okay. Yeah, that will happen here. So if the alternators are not connected to an infinite bus, uh, the system frequency will also tend to change. Right? Initially, the frequency will tend to change because the NR can change, right? That is the reason. Okay, so alternator A with increased torque input, because PE has increased. If PE has increased, right, that means I'm giving it more torque. PE has increased, so your delta is increasing. If your delta is increasing, that means what? Like previously, previously my NR and NS were here. Okay, so okay, previously your NR and NS were here. This was my NR. NR was equals to NS. NR was equals to NS. Now you are saying that you are increasing the torque, right, keeping the speed constant. So NR is constant, right? NR is constant. NR is constant. And also you are saying if you are increasing the torque, that means your developed power is increasing. That means your delta is increasing. If your delta is increasing, that means what? That means NR is constant. So delta has to increase. So NS has to increase. If NS has to increase, NS is proportional to frequency, so F will increase. So as it is connected, as it is isolated, so frequency also will increase basically. Okay, so frequency will increase basically. Okay, so alternator A with increased torque input will tend to speed up, that is the NS will increase, leading to an increase in the generated frequency. So basically speed up meaning NS will increase, not NR. NR is fixed, NS will increase, which will tend to increase the generated frequency. Okay, this difference will cause active power flow from the faster to the slower alternator, because again delta, active power will flow from the higher angle to lower angle. So delta E is greater than delta B. So from active power will flow from alternator A to the alternator B. The load angle between the excitation voltage of two alternators will adjust, and the excitation voltage of alternator A will advance relative to alternator B, higher angle, right? So there will be inter-machine power flow will be happening, and until a new equilibrium is reached, after which both the angles will be same and no power flow will happen. Okay, an inherent property of synchronous machine is their auto-synchronizing action. If one machine tends to speed up, it will act as generator and supply the power to the other, which will then act as a motor. Okay, so this alternator B will act as a motor because it is absorbing the power, right? Then Conversely, if one machine slows down, it starts acting as a motor drawing power from the other machine to accelerate. So to keep the frequency constant, basically, they will transfer the power. So ultimately frequency will become constant because power transfer is happening. So what will happen to the second case? So on no load, I am already discussing about isolated case, because for loaded case, of course, there will be load. VT cannot be operating in no load, right? Like in infinite bus. So for under loaded case, if I increase the prime mover input, not for a isolated system, for a like infinite bus, right? If I'm increasing the power, like torque, that means I'm increasing the power input. That means that alternator will supply more power. Okay, so increase active power share. So the machine whose torque input has been increased, that will uh, alternator will take larger power share. Okay, it will transfer the larger power output. So if the power output here is constant, let's say px, previously both were transferring px by 2, px by 2. Suddenly if the power input of one of the alternator has, or the torque input has been increased, now it will supply larger, pa will be larger than pb. Okay, and the sum of both of them, pa plus pb, will be equals to px. Okay, that's it. Consequently, its armature current IA will increase to supply this greater active power. Okay, so armature current IA also will increase to supply. So armature current of that alternator will increase basically to supply more active power. Okay, the power angle delta between the EF and the terminal voltage of alternator A will increase, of alternator B it will reduce. Alternator B, the power angle will reduce. Okay, the power factor of this alternator might also change. Okay, because it is transferring more active power factor will change, right? If I'm increasing, if I'm changing the torque input, the power factor will also change, potentially improving it will potentially move towards unity power factor uh, only, not, it is not like it will move towards leading or lagging. No, leading, lagging, it will not improve, it will move towards unity. Whichever one value it was, it will try to move towards unity, that's it, depending on the initial operating point. Okay, uh, yeah, mainly what will happen is the active power input will increase from the alternator, same as case of isolated, but in isolated basically speed change also happens. Same actually will happen in your what do you call, with your alternator as well. If they are connected to infinite bus, if they are connected to infinite bus, same thing can happen. Okay, uh, so one more thing, power factor will improve, so power factor of alternator B actually will worsen. PF of alternator A will improve, PF will worsen. So basically one key point that I want to explain, like it is a theoretical interview question that can be asked. Okay, interview question is that about AC versus DC output nature. Except for DC generators, almost all electrical energy sources you will see are rated as kVA, like inverters, all these things, where provides alternating current. And in this case, right, what will be the rating? Okay, except DC, everything is alternating. What shall be the rating of the machine? Okay, so these devices typically support supply power of sinusoidal This is especially true for equipment responsible for large scale power distribution in consumption. Okay, so generally the form of the power measurement is watts, right, in watts. But you will see in few machines like synchronous machines and your transformers, MVA is given. Okay, so power generations and large electrical machines actually are rated in MVA. Okay, because it includes both the megawatt and the MVAR component. But you will notice like machines will always be rated at MVA except DC machines, because DC machines, it is a DC machine, so active power can only flow, reactive power cannot flow. But your power plant in power plant, what happens, you will see it is a 100 gigawatt power plant, right? 100 gigawatt. So power plant is rated in gigawatts, it is not rated in MVA. Why? Because the input that we give in a power plant is active power, let's say steam water. How can I quantify how much power that does this steam contain? How can I quantify that in a hydroelectric power, how much power does this water contain? To quantify this, to quantify this, they are represented in watts. To quantify this, they are represented in watts. That's it. Okay. Now let's discuss about one more thing regarding the parallel operation. So if there is sudden change in the load output, what will happen? As I have discussed, if there is sudden change, if there is increase in the torque input, right, then the frequency slightly increases. Same will happen in case of output. If there is sudden change in the output, what is the torque equation? The torque equation, torque is proportional to PE minus PM. So if PM is has increased, torque will be negative. If torque is negative, that means NR will be reducing, right? Because d omega upon dt is negative, so NR will be reducing. If NR is reducing, basically the frequency also will reduce. So that's why you are seeing frequency slightly reduces if I'm increasing the this load. So that is a problem, and this we will try to resolve with the help of Droop governors. We'll discuss about that. This actually should be at the starting. So what are the conditions for operation of alternators? So this is same condition, ditto condition, same as transformers. Voltage magnitude must be equal, frequency must be same, phase angle must be 0, and phase sequence ABC must be same. Okay, this you already know. I don't feel I have to explain regarding this much. Okay, so now let's understand the speed governing control. So basically we know with increased load there is reduction in frequency. So what we want to do is we want to measure this reduction in frequency. So this kind of characteristics, right, is called as droop characteristics. This kind of characteristics is known as droop characteristics. And what we do is we actually take this reduction in frequency as an input to motor, as an input to the motor, to the governor, which then increases the input speed NR to bring the frequency back to F, right? Previously the frequency will become F dash, now it will go back to F, right? So we want to measure this quantity. So this quantity is known as droop, that is delta F upon delta PM. How much change there is on the frequency with respect to the change in the mechanical load connected, mechanical or whatever load we have connected. Okay, so that's why this is very important to us. So this we try to sense. So this is known as the droop characteristics. Okay, here it is known as the droop characteristics, where it will be a linear droop line that although it is not linear actually, It is non-linear, but to simplify our analysis, we make it linear. Okay, don't worry, we will solve a question, we will understand this better, like how this load sharing happens. Okay, governed by this load sharing, we will understand with a question. So this is the summary basically. So active power can be controlled, the input of the active power can be controlled by prime mover. So how can I control the reactive power? With excitation. Okay, I have not discussed here, but if I am changing EF, right, if I am changing IF, then I can make it over excited, under excited. That will change the amount of reactive power inside, generated inside the alternator, right? This we have already previously discussed, that's why I have not discussed it over here. This we have discussed, right? Over excited, under excited, nominal excitation. So we can basically control our IF to change our, we can control our reactive power by changing our excitation. Okay, and it is related to terminal voltage. So I told you, if I am changing Q is proportional to the delta V, right? So if I am changing Q, delta V is changing, that means the difference of the voltage is changing. Okay, so that's why we can control the terminal voltage with controlling the reactive power. Okay, this I have discussed in the previous lecture, I think, that reactive power is proportional to delta V. Okay, okay, and if here in case of a alternator, if the active power is changing, then the frequency can drop. If the load is increased, frequency can drop. Okay, that we have discussed why frequency will drop. And we will use synchronizing tools to synchronize our alternators. We will discuss how can I synchronize, because connecting two machines in parallel, right, is not an easy task. Both of them must have same phase sequence. I discussed the conditions. Both of them must have same phase sequence, same phase difference, same voltage magnitude. Okay, all these things should be present, then only they will be properly connected in parallel. So how will I control the speed control? How will I do the frequency control? It is controlled by a speed governor. We will see just now how it is controlled by a speed governor. Okay, so let's solve this question. So we have two generators rated at 120 megawatt and 250 megawatt respectively. So I have P full load 1 equals to 120 megawatt and 2 equals to 250 megawatt, okay, respectively, are running in parallel. Okay, they are running, both of them are running in parallel. The speed regulation governor Droop. Okay, I will explain what does it mean. Settings are 4% for the first machine and 3% for the second machine. So they are telling speed regulation. Do you remember what is speed regulation? It is same as voltage regulation, right? So speed regulation formula is basically n no load minus n full load divided by n full load into 100. Okay, now what is speed proportional to? We know speed equals to 120 by p. So speed is proportional to frequency. So I can rewrite this equation, f no load minus f full load by f full load into 100. That is equals to my 3%, that is 3. Okay, for that is equals to 4 for the first one, and for the second one it is 3. Okay, so how will the characteristics look like? So I will draw the characteristics and then I will explain. So this is, let's say, along this side P1, PL1, along this side PL2. Okay, and this is frequency. So again they are running in parallel, so both of them should have same frequency, right? They cannot have different frequencies. So the no load frequency will be same. They will like one machine will start from here. Okay, another machine will start from here. Now the difference will be that this will be much steeper than the other one. Why? Because you see the drop is much higher, right? Because the speed regulation is 4%. Speed regulation higher means as I will increase my load, the drop will be much higher. That's why it is more steeper than this. Okay. So this slope and this slope is the same? Actually not. It is not actually same. It is different. So here, what is the actual Droop slope? Do you remember what is actual Droop slope? So that is Droop actually is this delta F upon delta PM. So that is a different thing actually. So let me do this thing. So basically their no load full load voltage will be same. That basically means that if I am connecting here, then P1 is 120 megawatt. So this is the full load power, right? Okay, and of course their frequency must be same. So this is the F full load and this is the F no load. So here I know this point will be what, 120 megawatt at full load. Of course the generator 1 will deliver 120 megawatt, and here at full load it will deliver 250 megawatt, correct? 250 megawatt, the second generator. Now what is this slope actually? This slope, can I calculate this slope, value of slope? The value of slope is very easy to calculate. It will be F y2 minus y1, that is F no load, F full load minus F no load divided by F x2 minus x1, right? So here x2 is 120 megawatt, x1 is no load 0 megawatt, right? So it will be 120 minus 0. Okay, I'm keeping it in megawatt only. And for the left hand side again, this will be F full load minus F no load divided by 250 megawatt. That will be equals to I don't know what is it equals to. Okay, I don't know what is equals to, but I know this, right? F no load minus F full load into 100 for the first one. Okay, this is for the first one, is 4, right? So from here, let's assume that this is F no load 1, F full load 1, F full load 1. Okay, full load frequency must be same. Okay, no load frequency can be different, full load frequency must be same, because if they are operating in no load, then their frequencies can be different, that is fine. But full load frequency must be same, right? Because they are together operating in parallel. Okay, so this is the FL1, FLN1 minus FL2 equals to 4. So here, right, I can replace it over here, right? I can replace it. So this will be what? This value is what? It is just negative of this multiplied by FL into 4. So this will be minus 4 FL divided by 120. Okay, and here this will be what? If I write the other equation, it will be FL NL2 minus FL. So that is 3%. They have given me that is 3%, right? So this will be minus 3. Why negative? Because see, it is reducing, right? That's why the slope has to be negative. Minus 3 into FL divided by 250. Okay, this is the slope. Now when, let's say at a random point, because at full load this is giving 250, this is giving 120, so that will be 370, but that much power I don't need. I will need a power much earlier, somewhere here. Okay, somewhere here. So let's assume that at here FL2 is providing the power as PL2, and the alternator 1 is providing PL1. So I know PL1 plus PL2 overall power, they should be able to supply 200 megawatt, because they have told me that I am supplying 200 megawatt. Okay, so I have to supply 200 megawatt. That's it. Now one more thing is, will I be able to write out down this point? So at this point the frequency must be same. The frequency must be same. Now one thing I forgot to mention is that their no load frequency, as I told you, that can be different. Okay, no load frequency can be different. That is fine, because no load means they are not operating together, right? They are operating in no load. So no load frequency can be different, but full load frequency must be same, and operating frequency must be same. No load means it is not operating, right? So no load frequency can be different. Okay, so this is the value of f. Can I write f with respect to the right hand side line? So let me write the equation of line. What is equation of line? Equation of line is y equals to mx plus c, right? So what is y? Y is f here. Y axis is simply f, right? What is m? M is this value. This is the slope. This is the slope, right? So it is equals to minus 4 fl divided by 250, sorry, 120, plus 120 plus c. C means when I make the power 0, what is my, okay, sorry, oh sorry, the no load, no, sorry, I'm sorry, no load frequency also must be same, otherwise I will not be able to equate it. Sorry, I'm sorry, if I don't equate the no load frequency, that also will be different, right? Yeah. Or am I correct here? But if the no load and full load frequency is, no load frequency also will be same, sorry, they are operating in parallel. Sorry, no load frequency also must be same. If they're different, then I will not be able to solve this equation. Sorry, no load frequency must also be same. Okay, sorry. So like if I put here p equal to 0, then that is fnl, right? Fnl. Now if I write the same equation for the left hand side line, it will be minus, sorry, here, right, I forgot to write x. X is what? X is the value here, that is pl1. Forgot to write the x. So this will be minus 3 f fl divided by 250 PL2 plus FNL. I'm sorry, no load frequency must be same, otherwise I will not be able to, like, I will not be able to solve this equation, right? There will be 3 unknowns, then I will need another equation. So then I will equate this equation 1 and this equation 2. So trust me, no one will explain the Droop characteristics like this. Everyone will explain very difficult way, okay, which you will never understand, okay. So now I will equate these two lines, because f is same, frequency has to be same. So what we are seeing is FNL will get cancelled. So basically minus 4 f full load divided by 120 into PL1 will be equals to minus 3 f full load divided by 350 into PL2. So from here I can directly say what is my PL1 in terms of PL2. So PL1 in terms of PL2, 3 divided by 1000 into 120. So it is 0.36. Okay. 0.36. Okay. So from here I know what is PL1 plus PL2, right? If I replace here PL1 as 0.36 PL2, I will be able to get my 0.36 PL2 plus PL2 is equals to 200 megawatt. So it is equals to 1.36 PL2 equals to 200 megawatt. So plus 1 into 200. So PL2 is 147 megawatt. Okay, PL2 is 147 megawatt and PL1 will be 0.36, so which will be 52.94 megawatt. Okay, I think this will be 147.06. Okay, now now let's see the like what is the importance here. So they will both according to governor Droop. So governor Droop will do like, because governor understands the characteristics of this, understands the characteristics of this, governor has to adjust itself the input so that such that this alternator will provide how much amount of load. PL1 will be 52.94 and PL2 will be 147. So governor will take the feedback that how much droop there is, and depending on that feedback it will adjust that both alternators. So that is the task of governor. That's why this characteristics is very important. That's why we have governors. So it can adjust different alternators. If I don't adjust my alternators, right, what will happen is then the frequencies will be different, then there will be mismatch in the bus. So for both of the alternators to operate in parallel, this load must be equals to whatever we have calculated 52.94, and this one must be equals to 147. Okay, so governor will adjust the input power. Okay, so that is the importance of governor. Let's now solve the next question. Calculate the required percentage change in the no load speed setting of the generator 1 to achieve equal load sharing between the load units. Okay, so initially the no load initially the no load frequencies were same, but now they are telling me that how much change I need to produce in the how much change I have to produce in the frequency of the no load frequency of the generator 1, so that they are sharing the load equally. Sharing load equally means PL1 must be equals to PL2, that is equals to 100 megawatt. Okay, now their no load frequencies are different. If the no load frequencies are different, that is FNL1 is not equals to FNL2. Okay, now again can I equate the equations? This, yes, I will. Now what I will do, the difference will be, these equations will be, instead of it being FNL and FNL, it will be FNL1 FNL2. That's it. Okay, this slope will be same, droop will be same, droop will not change basically. Okay, so now they're telling me how much change I need to make. So these two will be equal, and I know what is PL1, right? So what they are telling me, they're telling me the calculate the required percentage change in no load speed setting. So previously, so generator 2 has still no load frequency as FNL2, right? If I am changing the no load speed, that means I'm changing the no load frequency. Okay, now they are telling me calculate the percentage change in no load speed. So what is the percentage change in no load speed? It will be N, the new no load speed, minus the old no load speed, divided by the old no load speed, into 100. This will be equals to, like, it is proportional to frequency. So F no load speed divided by F no load minus F no load divided by F no load into 100 percentage. Okay, so if I subtract these two equations, then that will be the delta F, right? So delta FNL. So okay, they are asking me what is the percentage change, equal sharing. So if I subtract again the equation 1 and 2, if I subtract the equation 1 and 2, or if I equate the both equations, basically what will I receive? I will get here basically minus 4F full load divided by 120 into 100 because PL1 is 100 plus FNL1 because the no load frequency has changed, and this is minus 3F full load divided by 250 into 100 again plus FNL. Okay, so now what is FFL? How do I find out FFL? So if I draw the Droop characteristics again, okay, here, right, this will now become FNL1. So if I want to write, so this will now become, yeah, FNL1. If I want to write my FFL in terms of FNL1, what will be the value basically? So I have got two equations, right? Two equations I have got. So okay, I will go into the next page only, otherwise you will get confused. So here, right, I have got two equations. So Droop characteristics will not change. So this F ln1 minus F FL divided by FFL equals to 3%, that we already know, right? Or 4%, right? For the generator one, it was 4%. Okay. So from here, I can find out what is my FNL or what is my FFL, right? In terms of FNL1, because ultimately here there will be one unknown. So basically, what do I mean is this FNL will go on the left hand side because I have to find out this. I have to find out this, right? So if I have to find out this, this FNL will go on the left hand side, this will go on the right hand side. So it will be FNL 1 minus FNL equals to, this will go on the right hand side. So into 100 divided by 30, this will be minus okay, 1 by 30 is there, 100 is already common, so this will be 3 by 250 only. Okay, so I need to find out what is FFL, right? In terms of FNL, then it will be cancelled. Okay, so from here I can easily find out, because I have to find out FFL in terms of FNL. Sorry, I have to find out FFL in terms of FNL, not NL1. So another equation I have, that is FNL minus FFL by FFL equals to 3 by 100. So my FNL equals to 103 by 100 into FFL, correct? So I will replace it. I will replace it over here. So this will become 100 by 103 FFL into FNL1 minus FNL into 100. So 100 will get cancelled. So I will get this value. So which I already have here, right? So I will divide this by FFL. So I will get back this. Remember, this is in megawatt also. So if mega gets cancelled. So from here I get this V2 equation. Equals to this, right? Not NL, sorry, FFL, right? So I will replace this value, same value over here. Okay, this whole thing. So 100 is cancelled. So 103. So this equation, the second one, a third one. Okay, I will rewrite the third equation. So third equation will become, this will be 103 into this value, right, into 100 into 1 by 30 minus 3 by 250. This will be my percentage. Remember, this is in percentage, right? Am I correct? Everything is correct, right? Yes. Okay, this will be the percentage. I will calculate this value. So this will be 1 by 30 minus 3 divided by 250 into 100. Okay, I have done something miserably wrong. That is what I am thinking. What have I done wrong? Okay, here this is 4 by 100. This is, okay, FFL goes there. FNL will be somewhat higher. That is correct only. Okay, this will be 100 at 103. So 103 at the go at the top. This will get cancelled. This will be this will go on that side. This will be 1 by 30. This will be 3 by 250 divided by FFL. Okay, 100 into this. What am I doing miserably wrong? That is what I'm trying to think. 103 2.100 extra is getting multiplied somewhere, because answer is 2.13. I know I've calculated the answer is 2.13. Somewhere like 100 extra has getting multiplied. Where is the extra 100 getting multiplied? That is what I'm not able to understand. 100 has been cancelled, right? This I will replace over there. Okay. Oh, sorry. Okay, this was, oh no, this was 3 by 100, right? So this will go on that side. This will get added. This is 103 by 100. That is correct only. Okay. So this will be 100 divided by, sorry. This is 103 divided by 100. Okay. F note is 103 divided by 100. What I've written it opposite actually. Sorry. Written it opposite. Three. Okay. So 103 divided by 100. Okay. And this is equals to 100 into this. How many hundreds are there? Okay, I made a huge mistake throughout the question. I'm really sorry. Actually, in the previous part, did not matter actually. So this FNL1 minus FL, right, was 4 by 100, not 4. Okay, I made a big mess, right? It is 4 by 100, not 4. I'm really sorry. I know you guys were screaming at me. This should be 4 by 100. Sorry. So this will be actually 0.04. That's what I am thinking. Why is that extra 100 missing? That extra 100 is gone somewhere, dude. So that it's 4 by 100, so it will be 0.04. Okay, I'm really sorry. It will be 0.04 FL into by 120, and this will be 0.03 FL. Okay, I'm really sorry. So actually here it did not matter, because both 1 by 100 were cancelled. Okay, I'm sorry about that. So this will be 0.04. This will be 0.03. Actually here it did not matter, because both of them cancel, right? 1 by 100, both of them cancel. So ultimately answer came out to be same. Okay, answer came out to be same. It did not matter over here, but here it will matter, right? Here it will matter. So actually this will be 0.04. I'm sorry. This will be 0.04. This will be 0.03. That's what I was thinking. Why is that extra 100 gone, man? Why is that extra 100 gone? So here, right, actually a multiplication also will be there into 0.01. So automatically this 100 and this one will get cancelled. Okay, into 0.01. So ultimately what I will be left with is, this will be 103 into this value, right? Whatever this value is. So it comes out to be 103, say 1 by 30 minus 3 by 250 into 103. Okay, so it comes out to be roughly like it is in percentage only, because remember it is in percentage, here it is in percentage only, so it comes out to be 2.197 percentage. So this will be your answer for the question. Okay, the answer for this question will be 2.197%. So this question was actually pretty elegant. So I will quickly explain what I did. Okay, so first of all, in the first scenario, if it is sharing 200 megawatt, they are telling me what will be the load shared between each of them. Now both of them have different group characteristics. So this has 4%, that means the speed regulation is 4%, right? So frequency regulation also will be 4%. Okay, I forgot to divide by 100 here, and the for the machine 3 it is 3%. Now I will draw the graph and I will assume that both of them has same no load frequency. If nothing is mentioned, I will assume both of them have same no load frequency, otherwise I will not be able to solve this equation. I will have 3 unknowns, right? And then I will just write the equation of the line. So for this, right, the droop will be the difference of the no load minus full load divided by the power, right, total power length, dy upon dx. Okay, so dy, how will I find out? From here it will be 4 into fl. Okay, and dx will be already given to me 120. Similarly here I will do, and similarly I will equate the two equations. They have to operate in same frequency, so I will equate the two equations, and from there I will get the other relation. PL1 plus PL2 already I know is 200, other relation I will get, and from there I will be able to calculate the load share. Now in the next phase they are telling me I will shift this graph, the right hand side graph upwards to make the slope different, right? So if I shift this graph to make the slope different, basically it will now share more load, it will be able to share more load if I shift the graph upwards. Okay, so it will be able to share more loads. It will be able to share more loads. Okay, that's it basically. So that's what we have done. So they are asking me what will be the difference, what will be the percentage change, right? Percentage change is this value, this is the percentage change in the no load speed, basically no load frequency, and from there I can derive what is my, like, again I will write the same equation, but this time I know the powers are same but this is different. Okay, so from here I will get one of the equations that will be equals to divide by fl. So ffl I will be able to find out from this equation. Okay, this is question actually is very tricky, and trust me, no one will solve explaining this much in depth, no one. Okay, so let's now solve the next question. So a 50 hertz isolated synchronous generator is rated at 15 megawatt. So the maximum capacity of the generator that the generator can provide output is 15 megawatt. Okay, which is also the maximum continuous power limit of the prime mover. So I cannot provide beyond 15 megawatt. Okay, very important point, because that will be useful to us. Okay, it is equipped with a speed governor of 5% droop. So basically if it is equipped with a speed governor of 5% droop, that basically means my FNL minus FFL divided by FFL into equals to 5 divided by 100. Okay, now what I can say is that this is my power, this is my frequency. Droop characteristics will be somewhat like this. Okay, so now if initially the generator is feeding 4 megawatts loads each at 50 hertz, so it is actually providing three three loads which are 4 megawatts each at 50 hertz. Okay, so I have three loads connected to the generator. Okay, three loads are connected to the generator. Each of them are 4 megawatts. 4 megawatts. 4 megawatts. And 4 megawatts. Each of them are 4 megawatts and is operating at 50 hertz. So currently, what is the total power delivered by the generator? 12, right? So it is delivering 12, right, megawatts, and I'm operating at 50 hertz. So from here, will I be able to find out the no load frequency? So what is the full load frequency then? That also I don't know, right? What is the full load frequency? So I know the Droop. So full load frequency is at 15 megawatt, which I don't know. I know the frequency at 12 megawatt. Okay, I know the frequency at 12 megawatt. So can I use this equation? Okay, so again I have to utilize the same equation, that is my FNL minus FFL equals to 0.05 into FFL, right? So one thing I can do is I know this equation, right? I know the equation, that this one, okay, FNL minus FFL. So can I use the property of similar triangles? Can I use the property of similar triangles? So how will I? So I know this is my FNL and this is my FFL. Okay, so I have a triangle here and I have a triangle here. So these are similar. So what I can do is I can write this equation. So triangle 1, FNL minus 50 divided by FNL minus 50 divided by 12 that is equals to F. So sorry, this will not be 12, right? So FNL minus 50 divided by, yeah, this is correct. FNL minus 50 divided by 12. So this is the first angle. The next angle is FNL minus FFL divided by 50. Okay. So do I know what is my FNL minus FFL? Yes, it is equals to 0.05 into FFL, right? So from here I will get the value FNL minus 50 is equals to 0.005 by 15. So from here I will be able to, sorry, here I have FFL, right? I will be able to say what is my FFL in terms of FNL, right? So it will be 15 divided by 12, 1.25. Okay, divided by 0.05 is also there. 25 into this, right? So 25 into this, 25 into FNL minus 50 divided by 12. So divided by 12 is already gone, sorry. So this is the value of FFL. Am I correct here? Oh, this is something wrong. Something is wrong. 15, 12 is there. This cannot be this low, right? FFL is there. Okay, okay, this is just the difference. Yeah, that's just the difference. No, this is correct only. Yeah. Am I correct here? I will just quickly check. 15 divided by 12 divided by 0.05. Yes, 25. Correct. Okay. So this is my FFL basically. Okay. So now I will replace my FFL here. So I can directly say what is my FNL equals to 1.05 FFL, or I can replace my FNL here as well, whichever one is suitable to you. But okay, let me replace FFL here only. So if I replace FFL here, so my FNL is equals to 1.05 into 25 into FNL minus 50. Okay, so this will be, from here I will be able to find out my FNL, right? So into 1.05 and subtracted by 1. Okay, so 25.25 FNL equals to, now this will be 1.05 into 25 into 50, 1312.5. So this divided by 25.25 gives me, so FNL, right, is equals to 51.98 hertz. Okay, these questions are actually pretty good. So what will be my FFL? FFL will be equals to this, right, this value. So it will be this minus 50 into 25, which is 49.5 hertz. Now, okay, let's now come back to the question. So now they're telling me that if the generator is feeding this loads, one of this is programmed to trip permanently if the frequency falls below 48 hertz. Okay, if the frequency will fall below 48 hertz, it will trip permanently, but it will never fall below 48 hertz because frequency full load, that is at 15 megawatt, the frequency is 49.5 hertz. So it will not fall below 49.5 hertz. Now what they are asking, if an additional load of 3.5 megawatt is added, connected, then the frequency will settle down to what value? What will the frequency settle down to? That is what they are asking, right? So important point to note here is that I'm adding an additional load of 3.5 megawatt. Okay, if I add an additional load of 3.5 megawatt, what will happen? Obviously frequency will reduce, that much is I'm sure about that. Frequency will reduce. Okay, this will be 3.5 megawatt. Now if I see the overall load, now it becomes 15.5 megawatt. So not possible, not possible, right? Not possible, because given in the question they have given me that it will maximum it can provide is 15 megawatt, that is the maximum limit. So one of the load has to be disconnected. If one of the load is disconnected, now the power is basically 4 plus 4 plus 3.5, that is 11.5 megawatt. Now the power becomes 11.5 megawatt. I know there is confusion, the question could have been better, more clearer, but that is what we have got, right? That is the only option. Okay, so what I can say is that so now I will calculate the frequency. So again I know the droop now. What is the droop? Droop is f no load minus f. So this, right, this will be what I have found out. What is f no load? F no load is this value 51.98. So 51.98 minus full load, that is sorry, minus 50 divided by the power, that is 12 megawatt, right? That is the droop. Okay, so I got my slope m. Sorry, so this will be 50 will come first, then 51.98 will come. Okay, so I can directly write my frequency. What will be the frequency? It will be this droop, right? 50 minus 51.98 divided by 12 into the power. Power is basically 11.5 megawatt plus the no load frequency. No load frequency is 51.98 only. From here I will be able to find out my operating frequency. That is what they are asking, right? At what frequency it will operate, settle down to. So this will be 51.98 minus 50 divided by 12 into 11.5. Okay, should be negative, right? Sorry, 50 minus 51.98 divided by 12 into 11.5 plus 51. So the frequency comes out to be 50.0825. That is the frequency. Okay, so this will be your answer. Frequency will be 50.0825. So that is present in option C. So option C will be the correct answer. Okay, I hope you have understood this question. These questions are actually pretty difficult, not that simple, and everyone will solve some formula. You will never understand that. You will never understand that. Okay, so what is the synchronizing procedure? Before that, before synchronizing, we need to understand what are the conditions for proper synchronism, right? So and why we cannot connect a stationary alternator. If let's say the alternator is stationary and I connect it to the incoming infinite bus bar, what will happen? A stationary alternator must never be connected directly to a live bus bar if its terminal are connected without matching the voltage phase, and then what will happen? Basically a large short circuit current will flow because this has not developed any potential and this has high potential like VT potential. So a large current will flow through the alternator. It will behave as if it is a motor. Okay, and if it is connected to no load, so huge current will flow. That is known as the large short circuit current. Okay, uh, flow due to absence of synchronization. If it is not properly synchronized, large short circuit current will flow. Okay, so potentially damaging the alternator or the system. So it will damage the alternator or the system. Okay, conditions for synchronization. Before connecting an alternator to the grid or another machine, the following essential conditions must be fulfilled. Okay, first condition is they must have equal voltage magnitude, they must have equal frequency, the frequencies must match, their voltage magnitude must match, their phase sequence must match. If their phase sequence is different, then there will be phase difference, right? So all this already we have discussed in transformer, so that's why I'm going very fast over here. And their phase difference also should be zero between them, right? If there is phase difference, then power will flow, there will be a circulating current, right? Power will flow from one alternator to other alternator. This already we have discussed, I don't think we have to explain it over again. So I want to connect already a system is running, I want to connect this alternator to the system. So how will I connect it? So there are many methods of connecting. The first method is using lamps. Okay, you might say, sir, lamps, how lamp will help? Lamp will help actually. So let's say I am connecting the infinite incoming alternator to a infinite bus. Okay, and let's say the lamp is connected like this. So this point is VA dash, and let's say this is the E phase of the alternator, this is the B phase of the alternator, and this is the C phase of the alternator. Okay, and for a second let's assume that the alternator is developing a potential voltage that is not exactly equals to the frequency of the incoming bus bar. Okay, both of them are different. So VA will be what? VA will be, let's assume that the magnitude is same, right? Magnitude is same, but there is slight frequency difference. Okay, this is our assumption, there is slight frequency difference. So VA will be VM, let's like you can take sine or cos, sine and cos are both same, but we will take cos omega t for easier mathematical operation, that's it. Okay, sine and cos are both the same waveforms, just phase shifted by 90 degrees. So VA is VM sine cos omega t, and VA dash, let's say assume that the frequency is not exactly same, it is VM into cos omega dash t. Okay, that is what my VM is equals to. I hope you have understood this point. Now what is the potential difference across this lamp? That will be equals to VA dash minus VA. Okay, so VM into cos of omega dash t minus VM cos omega t. Okay, so this will be equals to Vm into cos omega dash t minus cos omega t. So it is cos A minus cos B. Okay, so cos A minus cos B. What is the formula for cos A minus cos B? If you remember, okay, I also don't remember. I also do Google search. So cos A minus cos B is 2 sine A minus B divided by 2 into sine A plus B divided by 2. Okay, this is the formula for cos A cos B, right? So yeah, I will replace this over here. Okay, so it will become, so even though there is no phase difference, there is just frequency difference. Assumption is there is no phase difference, just frequency are different. Okay, then this will become 2 sine of A minus B divided by 2, that is omega dash minus omega divided by 2 into sine of A plus B divided by 2, that is omega dash plus omega divided by 2. Okay, so into t obviously will be there, into t is common, right? T will be there, omega t, this t will be there. Okay, so yeah, if I cannot this t is in between, so okay, so what do I notice? Actually, I notice that I am like the potential of Va minus Vd, that is a lamp potential that I am getting, does not have a frequency of omega. It has two frequencies. One is this omega dash minus omega by 2, one is omega dash plus omega by 2, right? So what is happening basically, remember omega, like omega, let's say omega dash plus omega will be very larger than omega dash minus omega. So this divided by 2, this divided by 2, right? I'm subtracting and I'm adding, and both are positive quantities. So of course this will be much larger than this. Okay, so this has higher frequency, right? What does higher frequency basically means? Higher frequency means the time period will be much lower for this waveform. The time period for this waveform will be much lower than the time period for this waveform. So this waveform will be very fast, higher frequency, very fast, and this waveform will be very slow. Okay, so basically the graph, if I plot this, right, this let's say is omega t. So first I will plot this one. First I will plot this one, omega minus omega t divided by 2. So this will be a sinusoidal, but a very slow sinusoidal. Okay, very slow sinusoidal. Okay, so okay, so this frequency is known as the omega minus omega dash. Now this will be a envelope, this will work as an envelope to this. Okay, there are two sinusoidals, right? This will, like, I'm multiplying two things. So this has a frequency of, sorry, this has a frequency of omega dash minus omega divided by 2. So this frequency is omega minus omega dash divided by 2, sorry, omega dash minus omega divided by 2, yeah, omega dash minus omega divided by 2, right? And I will actually mirror this, I will mirror this graph. Let me mirror this. Yeah, Okay, let me mirror this. Okay, so now what I will do is that this, what is the frequency of this will be much faster, right? This will be much faster. So I have, just hold on, give me 1 second. So I will do this later because otherwise you will get confused. So let me keep it here. Okay, and let me copy this. Like this is product of two voltages. Let's say this is voltage Vx, this is voltage Vy, right? So let me plot the two voltages. So Vx will be this. Okay, this is my Vx. What is my Vy? So Vy will be same, a sinusoidal only, but its time period will be much faster. Time period will be much faster. Okay. So basically, yeah, I will have more sinusoidals. I'll have more sinusoidals, right? So this frequency will be, I will change the color. Omega dash plus omega divided by 2. Now I am multiplying these two. I'm multiplying these two. So I see it is positive, this is also positive. Then again it becomes negative. Negative times positive will be something negative, right? But remember I'm multiplying these two, so this amplitude is also increasing, right? So it's basically, it is just like a, if I write this, right, it will be basically V m of t into sine of omega dash minus omega divided by 2t. So basically what is happening, its amplitude, right, Vm, that is a sinusoidal function. So its amplitude also will vary. So I hope you remember how to multiply two functions. There will be envelope. So this is the envelope basically. The slower one will be the envelope always. Slower one will be the envelope, and its amplitude is also changing. So the graph will be somewhat like this. Multiplication product will be somewhat like this. Okay. You try to plot this in the Desmos, you will see you are getting the same value. This I think we have discussed previously as well. If I am multiplying two sinusoidals, why is this interesting? I will discuss. So there are a few terms here. So this, right, this term is called as the beat frequency, and this is called as the carrier frequency. Carrier frequency because it carries, and it's a communication term. But why is it called beat frequency? Why is it called beat frequency? It is called beat frequency because basically my lamp, right, if you see the lamp, how the lamp will go. So in the initially here at this position, the lamp will be slight dim. Okay, like I will show you. Lamp is dim. Okay, lamp is very dim, very small voltage. Lamp is dim here, right? At this position, the lamp is dim. At this position, the lamp is dim. Then slowly the amplitude increases, so the lamp will glow. Like RMS value is increasing here, right? RMS value is increasing. Lamp will glow. Lamp is still glowing. It will slightly dim. Then again it goes to zero. Then again here lamp again starts to glow because amplitude is increasing. Then again it starts to dim. Okay, so that's why it is called beat frequency, because at this frequency the lamp beats. It beats, right? Because one glow and dim is known as a beat. Okay, one glow and a dim is known as beat. Okay, so at this frequency the lamp will beat basically. So initially it is glowing slowly. Then again it is decreasing. Again it is glowing. Again it is decreasing. Okay, so this actually this term defines how many times my lamp will glow and dim. Okay, lamp will glow and dim. So that's why this is called the beat frequency. And carrier frequency because it is just like a carrier signal. That's why it is called as a carrier frequency. Okay, so the amplitude is like changing across the bulb. If the amplitude is changing, of course the brightness of the bulb will change. So I will say amplitude of voltage changing across the bulb, then amplitude of voltage changing across the bulb, then the brightness also will change. So this is how basically how we'll understand that whether our bulb is properly, whether our machine is properly synchronized or not. So can you tell me, if the machine is properly synchronized, what will happen? Then this beat frequency will be 0. Then omega dash and omega will be 0. So at synchronism, omega dash will be equals to omega. So bulb will never glow. So bulb will always be dim. Bulb will always be dim. Okay, so that is what will happen. Bulb will always be dim no matter what. Okay, so yeah, I hope you have understood this point. Yeah, now let's do one thing, that that is what is happening over here. Yeah, so bulb will always be dim, it will never glow if it is properly synchronized. So from this we understand, like we will understand, if I'm connecting the, if I'm not connecting the incoming alternator bus, I'm just connecting one of the phases and the other phase to the lamp, right? And if the lamp is glowing and stopping, that means that there is frequency difference. Now it will beat very fast, it will glow and dim very fast if the frequency difference is very high, right? So if omega dash minus omega divided by 2 is high, that is bulb will beat very fast. Bulb will beat very fast. Okay, hence bulb will beat very fast. Hence I can say that the difference omega dash and omega difference is very high. Difference between the frequencies is very high. Okay, difference between the frequencies is very high. But will I be able to tell which one is higher and which one is lower? How will I be able to tell, like, which frequency is higher and which frequency is lower? Like, it can go both ways, right? Omega can be higher, correct? So how can I say? So if after increasing omega, if I increase omega and the rate of beat and the like basically beat reduces, right? Now it is slowly changing. Okay, if I increase the omega and beat reduces, that means my basically my omega dash was greater than omega. Why? Because if I increase omega, that means this difference is reducing. That's why the beat reduces, because this difference will reduce, beat frequency will reduce, so the bulb will glow and dim at a slower rate. But if I increase omega and beat increases, that means what? If I increase omega and beat is increasing, that means my omega is greater than omega dash. How? Let me take an example. Let me assume that omega dash is 1 and omega is 0.5. Okay, just a number. So if I increase omega here and I see beat is reducing, that means 1 minus, let's say I did 0.75, so it is reducing 0.25. So 0.25 is the beat frequency which has reduced. Previously the beat frequency was 0.5, so it has reduced. So that means, is omega dash greater than omega? Yes, I am observing omega dash is greater than omega. But let's take another case. Let me take omega dash equals to 1, omega equals to 2. Now if I increase omega, let me say omega to 3. Now what is the difference? Previously the difference was 1, now the difference has become 2. So the beat frequency has increased. The beat increases. That means my omega is greater than omega dash. Exactly, that is what I have written. That is the conclusion. Okay, so that is how you will be able to understand whether the incoming bus bar frequency is higher or lower. Okay, so these are the things that you need to take care of. Okay, I hope you have understood exactly. So these are the only things that you need to take care. Okay, these are the only things that you need to take care. Now all this was the case if there is no phase difference. So if the frequencies are same and there is no phase difference, then all this would have happened. Okay, so all this we have discussed if there is no phase difference. Okay, if, like, whatever case we have discussed, that phase difference is 0, frequencies are different. So this was the case 1 where frequencies f is different and your phase difference is 0. There is no phase difference, but frequency is different. Okay, so basically I want to discuss if there is phase difference. If there is phase difference and frequency is same, right? If phase difference is there, phase is different between the two phase, between the incoming and the existing bus, frequency is same, so this we can understand with phasor. So here let's say this is VA dash. Okay, amplitude everything is same and frequency is same, right? I can draw in a same phasor diagram. This will be my VA. So there is a phase difference, right? Theta. So if there is phase difference, of course there will be a constant voltage that will appear across the bulb. How? So again, if I do VA dash minus VA, I will get Vm sine omega t minus Vm sine omega t minus theta. Theta is lagging, right? So omega is same, frequency is same. Again, I will take Vm common. Sorry, I will make it cos, right? Cos is easier for us to calculate. Cos. So this will be Vm into 2 sine A plus B into sine A minus B. Sine A plus B is sine 2 omega t minus theta divided by 2 into sine A minus B, that is sine A minus B, t is there, sine of A minus B, that will be sine theta, simply theta divided by 2. So what we are saying, we are observing it is a sine function but frequency is same, same, right? It is what? Omega t minus theta by 2. So frequency is omega only, sorry, this is not omega t, frequency is, so this will be omega t only, sorry, this is what I am doing, this will be omega t, this here t will not be there, this will be omega t only, right? Yeah, so frequency is omega only because I am dividing by 2, right? So it is omega t only. So frequency is same, just this amplitude is constant now. It is not a function of frequency, it is not a function of time. So I am getting a sinusoid. It is just like some Vm dash sine omega t minus theta by 2. So I am just getting a constant voltage appearing across the bulb. So bulb will simply glow. Bulb will glow. That's it. Bulb will glow. Okay, but it will not flicker. In this case, bulb plus flickering, right? Here bulb was flickering. So bulb will flicker. Bulb will flicker. Okay, bulb will flicker. So now if I say, if both are different, if phase and frequency both different, we'll observe both of this phenomena. Bulb will glow plus flicker. It will glow brightly and it will flicker as well. You will see bright glow and flicker. If everything is same, bulb will be turned off, bulb will never be on. So this is the method of checking synchronism of alternators. Ensuring that an incoming alternator is in perfect synchronism with the existing power system, it is critical, right? So this is the first method, that is synchronizing by dark lamp method. So this also has two sub methods that I will discuss later on. Okay, that I will discuss later on, but the concept is same. Whatever concept I have explained here, that will be utilized. Okay, so we have three incandescent bulb, and there are two common connections. One is dark lamp method, another one is bright lamp method. So we will see which one works. So lamp are connected across the switch, and bright lamp method is where lamps are connected in opposition. Okay, so opposition meaning same phase lamps will not be connected. Basically this point will be connected to phase A and this point will be connected to phase B. Okay, that also we'll see, but ultimately the concept will be same. Okay, so you see working principle, the voltage across each lamp will be the vector difference, this omega to omega 1. So if you do this, you will see that I'm getting two terms. One will be f1 minus f2, another one will be f1 plus f2. Okay, if the frequency difference is high, the lamps will glow and dim, that is flicker at a very fast rate. This frequency difference is very high, it will flicker at a very fast rate. If the frequency difference is low, the lamp will glow and dim at a very slow rate. So like this we can understand how close or how far I am with respect to synchronism. Okay, if I am very close to my supply frequency, or if I am slow, if I am very far away from my supply frequency. If increasing the speed of the incoming machine causes the flickering of the bulbs to increase, it indicates the frequency of the incoming machine was initially lower. This already have explained here. Okay, I will not repeat. I have already explained here, so I'm not repeating again. Okay, same thing it is writing over here. Phase difference, if there is no phase difference and frequency are equal, the bulbs will completely be off, that is dark. If there is phase difference, bulb will glow steadily, it will not flicker. Okay, if both phase and frequency difference is there, the bulb will glow and flicker. Okay, I hope that point is clear. Already we have discussed regarding this. Advantage, how do I check phase sequence? Because this method, right, you don't have any way to check the phase sequence, because you are only comparing one single phase. So to check the phase sequence, you need to have you need to connect the three lamps. So if the three lamps do not flicker together, that is they don't all go dark or bright at the same time, it indicates that the phase sequence of the incoming machine is improper. So basically because why, I will connect the three lamps together with their respective phases. So if the phase sequence of the bus bar is ABC, and if the phase sequence of the incoming alternator is ACB, what will be the problem? I will connect A with A, I will connect B with C. Why? Because like my phase sequence is difference. Okay, sorry, I will connect B with B, I will connect C with C. But here, right, there will be a problem, because what is the phase difference here? This is 0 degree, this is 120, this is 240. What is the phase difference? This is 0 degree, this is 120, this is 240, right? Okay, but I am connecting B with B, so there is a constant phase difference between B phase, right, in the B lamp, and there is a constant phase difference in the C lamp. So they will not flicker or glow, right? They will just glow brightly because there is a constant phase difference. If the phase sequence is different, then they will not flicker together in sync. So by this we can understand that the phase sequence is opposite. I have to change the phase sequence. Okay, I hope that is clear to you. There is a constant phase difference between the bus bar and the incoming alternator. Okay, advantages, cost effective. It requires only simple incandescent lamps. It requires only simple incandescent lamps. Okay, so that is the advantage of this because it is not very costly, right? It is very cheap. It is very cheap, and no dedicated phase sequence device required. The differential flickering indicates an incorrect phase sequence. If there will be a differential phase difference, you will see that the phase sequence is incorrect, right? So in this method, we don't need a separate phase sequence device. In synchroscope, we will need a separate phase sequence device that we will observe. Okay, so disadvantage. So when will I actually connect the bus bars? When will I connect the bus bars? I will connect the bus bars at this point, right? At this point, when voltage across the lamp is 0, right? Slowly increase the potential, and of course there will be always certain potential like frequency difference. You cannot make it exactly equal, so that will always be there. So slight flicker will always be there. I have to close the switch, right? Close the switch of the bus bar. I have to disconnect this lamp and close this switch at this point. When the bulb is just turning on, at that instant I have to turn it on. So actually it is very difficult to do that. It needs a experienced person. Okay, so difficulty in judging the exact synchronism, because at that point the synchronism will happen, right? At that exact point when the bulb is almost dimming. Okay, incandescent bulb do not light up instantly. So basically if I'm providing, let's say it's 100 volt, right? It's a sinusoidal voltage, it will not instantly glow. Okay, it will take some time. So it needs a experienced person who can estimate and understand when the bulb is going to dim and when it is brightening up. Okay, so instantly light up or go completely dark even when small voltage is applied across it. Okay, it does not go completely dark, right? It does not go completely dark. Sorry, it will go completely dark. Sorry, I told you differently. So even if I am providing 10 volt, the bulb will completely go dark. Okay, because bulb has kind of a threshold voltage, just like diode will turn on if the voltage is 0.7 volts, right? Otherwise it will never turn on. Same for bulb, if the potential is below a threshold voltage, that is 10 volt or 20 volt, the bulb will directly dim, it will not light at all. So I am not able to find out the position exactly this zero crossing, right? So it needs a experienced person to understand and close the switch. Okay, so this makes it extremely difficult for an operator to precisely estimate the exact instant of zero phase difference when the bulb is truly dark. Okay, I have to identify the exact instant of zero phase difference, right? Then only I can close the switch. Okay, so it requires experienced personnel. Voltage sensitivity already we have discussed. Cannot directly determine the relative speed. So whether omega dash is higher than omega or omega is higher than omega dash directly cannot I determine. But if I change the alternator frequency and then observe whether the beat frequency is reducing or increasing, I can determine. So indirectly I can determine, but directly I cannot determine whether omega dash is greater than omega or omega is greater than omega dash. Okay, maximum voltage consideration. Of course, if the phase difference is very large, voltage across the lamp also will be very large. That can damage the lamp. So we have to be very careful regarding the rating of the lamp. Okay, so it is crucial to ensure that the voltage rating of the lamps is maximum possible voltage difference, that is twice. Why? Because let's say if the phase difference is 180, then you will see the voltage difference will be Vm of minus Vm, so it will be 2 Vm. Okay, it will be 2 Vm. Okay, so this should be the rating of the bulb, so that will increase the cost. That's it. That will increase the cost. Okay, that's it. Now let's synchronize by synchoscope. So this is the second method where I will synchronize my bulbs with synchoscope. Okay, so the synchoscope is a more advanced and precise instrument designed specifically for synchronizing alternators. Okay, so synchoscope is a more advanced. It is just like an electronic tool where I will just connect the synchoscope to the bus bars and I will be able to determine the phase difference. So what I will do is I will show you. It is just a electronic device. Okay, I don't have enough space over here, so lamp I will remove. Now what I'll do with the phase, right, I will connect the synchroscope. Okay, so synchroscope, what it does is it will take uh, two phases. Like there will be two phases, so it will take two phases. Let's say this phase and this phase. And the other two phases will be here. This needs to be here actually. This can be here and this can be here. Okay, so here I have let's say this is A phase, A1 B1, and this is, let's say, A2 B2, and this is my synchroscope device. So synchroscope is nothing. I will tell you what is your synchroscope. Synchroscope, so it will just simply compare the phase difference, that's it. Okay, so synchroscope is this. Synchroscope, right, will have a pointer which will indicate whether I am, like, the left hand side of the pointer will be slow and the right hand side will be fast. Right hand side will be fast, left hand side will be slow. So it will just simply indicate whether the incoming bus bar is fast or slow. Fast or slow meaning speed is proportional to frequency. So it will just indicate whether the incoming bus bar is fast, incoming alternator is fast or slow, that's it. It's just a device, it will directly compare. No bright lamp, no dark lamp, right? So a synchroscope is an electronic device with a pointer that rotates. It is connected across the same points as the synchronizing lamps, measures the voltages of the incoming bus bar, incoming machine and the bus bar, and pointer. So the pointer of the synchroscope rotates when there is a frequency difference between the incoming bus bar. So it will rotate on the right hand side if the incoming bus bar is faster than the infinite bus bar. Incoming alternator is faster than the incoming bus bar. It will rotate on the left hand side anti-clockwise if the incoming alternator is slower than the infinite bus bar. Okay, so same thing is written over here. Phase indication, the pointer indicates the phase angle difference. Okay, the pointer, when the pointer is at 12 o'clock, so basically if the pointer is not rotating, right, it is just stationary at 12 o'clock, that signifies the voltages of the incoming machine and the bus bar are exactly in phase. Okay, the idle moment to close the circuit breaker is the point when the pointer will be just pointing at 12 o'clock here, right? Then the phase difference is 0. If let's say the pointer is stationary, it is not rotating, but it is right hand side, that means there is a phase difference of whatever is the angle, right? Let's say this is 30 degree or something, so phase difference will be 30 degree. Okay, but there is a problem if there is large frequency difference, right? Behavior with large frequency difference, if there is very large difference in the frequencies, the pointer might not rotate smoothly due to the pointer's inertia, because it has to rotate very fast. Right? It will not rotate at all smoothly. Okay, it will just vibrate and oscillate. It will not rotate at all if the frequencies difference is very large. Okay, so actually it is not able to indicate the large frequency difference. So if there is large frequency difference, I should never connect the synchroscope. First I should at least try to reach to my infinite bus bar, the frequency, and then I should connect the synchroscope. Otherwise it will not work. Okay, advantage, it is highly accurate, It is an electronic device, very efficient, very accurate, easy to operate. Just a pointer is there, that's it. Don't have to think that okay, bulb is beating, glowing, something like, no. Simple pointer is there, you will be able to see it. Indicates lead lag, whether my incoming bus is faster or slower. I am directly able to see with the pointer rotation, right? Reduce risks, minimize the risk of transient currents. Okay, better, but it will be highly costly. Why it will be highly costly? Because it is more expensive system than a simple lamp. Lamp is very cheap, requires voltage equality. So first of all, I will not be able to compare the voltage, right? Voltage must be same. Peak voltage of both the phases must be same. That for that we need to connect a separate voltmeter. We need to connect a separate voltmeter to compare the peak voltage. So that will be again increase the cost. Phase sequence check still needed. So phase sequence it is not able to say. So we need to check the phase sequence. Phase sequence we need to check. So again it will increase the cost. So that is a summary. Basically we use lamp as a synchronization, or we can use synchroscope, or there are, like nowadays there are automatic synchronizers. Okay, we don't need this. Obviously for power systems, bigger systems, we have automatic synchronizer. So this is a summary. Basically what will happen when frequencies match, frequency is different, phase sequence is wrong. Okay, what will happen? Okay, this is a summary. So that's it basically for this lecture. So this was like the ending part was mainly theoretical, initial part was numerical. That parallel operation is actually very important. Okay, so with this we end our synchronous machines. Okay, one more topic is left. One more topic, that is harmonics, construction and harmonics. We have not discussed about harmonics in synchronous machines. So we will discuss about harmonics in synchronous machines. Also we will discuss about different types of single phase motors, and with that we will be ending our machines. If you enjoyed the machines subject, whole subject, make sure to hit a like button, make sure to comment down below on the videos. That will really help us out. Thank you, and I will see you in the next lecture. Until then, happy learning.